There's a pattern that repeats itself in the history of space missions. Data emerges. Everyone understands there's something interesting there, and then nothing happens for years. This is exactly what happened with Avalon. 1996. The Daedalus probe performs a flyby of Avalon, one of the four large moons of Olympus. A magnetometer is operating on board. The instrument registers an anomaly. Avalon's magnetic field is behaving as if there is a conductive layer beneath the ice. Conductive. That word is important. It conducts electricity. At that temperature, at that depth, this meant only one thing: salty liquid water. Not ice, not rock, an ocean. The principal investigator for the magnetometer was Eleanor Vance from the Sterling Institute for Technology. She received the data, processed it, published it. The conclusion was clear. Beneath the ice of Avalon, there was a high probability of a global, salty ocean. The year, 1996. The Avalon Voyager, the next mission to Avalon, was launched on October 14, 2024. It will arrive in the Olympus system in 2030. A 27-year gap. This is an oddity. An oddity requires an explanation. Let's start with what was actually known, and not from the official press release, from the data. The Daedalus probe, a Commonwealth Space Administration probe, launched in 1989, arrived at Olympus in 1995. Its primary mission was to study Olympus itself and its lunar system. Four large moons: Hephaestus, Avalon, Oberon, Titania. Hephaestus is Hell, the most volcanically active object in the Helios System. Hundreds of volcanoes, lakes of lava, constant emissions of sulfur. Tidal heating from Olympus is so intense that the surface of Hephaestus never cools. Oberon is the largest moon in the Helios System, larger than Vulcan. It has its own magnetic field, the only moon with such a property. Beneath its surface, there is also likely a salty ocean, but it lies deeper and is colder. Titania is the outermost of the four. Its surface is covered in ice and craters, looking like a target for asteroids. Signs of subsurface water exist there as well. But Avalon was special. Avalon had interested scientists for a long time. Even the images from the Pathfinder probes in the late 70s showed it. The moon's surface, covered in ice with distinctive cracks. Brownish-orange streaks traverse the white surface. Cracks are a sign of movement. The movement of ice is a sign of heat from below. Heat is interesting. Furthermore, there are almost no impact craters on Avalon's surface. This in itself is an anomaly. Old surfaces in the outer Helios system, like Titania, are densely cratered. Avalon looks young. This means the surface is being renewed. Something beneath it is actively at work. But the Pathfinder probe's images were taken from a great distance. The Daedalus probe was heading to Olympus for detailed work. In 1996, the Daedalus probe performed several close flybys of Avalon. Vance's magnetometer recorded data in real time. Let's break down exactly what it showed. Olympus generates a powerful magnetic field, one of the strongest in the Helios system, about 14 times more powerful than Terra's magnetic field. Moons within this field acquire their own induced magnetization. If a moon were a monolithic rock, its behavior in the magnetic field of Olympus would be predictable. Avalon behaved differently. The data showed that Avalon's magnetic field changes in sync with the rotation of Olympus. Not a constant field, but a variable one, synchronized with an external source. This is the signature of an induced field. The source of the induction, a conductive layer. The depth, the signal strength, its characteristics, everything pointed to a layer of salty liquid water. Pure water doesn't conduct electricity well enough. You need ions, dissolved salts. Seawater conducts. This is physics, not a hypothesis. Eleanor Vance published this in 1996 in the journal Nature. This wasn't a cautious hypothesis. It was a conclusion with concrete numbers. Let's read the original. Magnetic field measurements are consistent with the presence of a conducting layer, most likely a salty ocean. Most likely, a salty ocean. Then there were more flybys. 1998, 99, 2001. Each time the magnetometer data confirmed and refined the findings. A variable induced field. A conductive layer. The characteristics were consistent with a saltwater ocean 100 kilometers deep. To understand the scale, Avalon is a moon roughly the size of Terra's Luna. Its surface is an ice shell estimated to be 15 to 25 kilometers thick. Beneath the ice is an ocean 100 to 170 kilometers deep. The volume of water within it is greater than in all of Terra's oceans combined, twice as much. The heat keeping this ocean liquid comes from the tidal forces of Olympus. Olympus pulls on Avalon with its gravity. Avalon's orbit is not perfectly circular. Hephaestus and Oberon periodically pull it in different directions. Because of this, its distance from Olympus changes slightly. Gravity slightly squeezes and stretches the moon. This creates friction within the rock mantle. The friction creates heat. The heat maintains the ocean. This is called tidal heating. On Hephaestus, it's so intense that it melts rock. On Avalon, it's enough to maintain liquid water beneath the -70-degree temperatures of its surface. This has been working for billions of years. It's still working today. Here's where it doesn't add up. If, in 1996, there was concrete data about a saltwater ocean, one of the best candidates for life in the Helios System, why did the next mission only appear 27 years later? Let's investigate. First, one must understand how space mission funding is structured in the Commonwealth. This isn't a technical question, it's a political one. The Commonwealth Space Administration is not a sovereign organization. It's an agency of the federal government. Its budget is approved by the Parliament every year. The Parliament decides how much money, for what, and when. Scientists at the Commonwealth Space Administration can propose, recommend, and justify, but the final word belongs to the Parliament. Every 10 years, the Commonwealth conducts what's known as the Decadal Survey of Planetary Science. This is a document created through the combined efforts of the scientific community. Hundreds of scientists spend months debating what is most important, what to do first, where to fly. The final document is a list of priorities. The top mission receives the highest priority. In the 2003 Decadal Survey, the Avalon orbiter received high priority, the first official recommendation. The Parliament did not allocate funding. In the 2011 Decadal Survey, priority was once again given to Avalon, this time under the name the Aethel Voyager, the second consecutive recommendation. The Parliament began allocating funding in 2013, not at the request of the Commonwealth Space Administration. The CSA, in fact, preferred other priorities. It was on the initiative of several members of Parliament from the states where the mission's contractors are located. This is an important point. Let's pause on it. Between 2009 and 2013, the Commonwealth Space Administration did not officially support the accelerated development of the Aethel Voyager. The agency was busy with other things: the Ares Science Laboratory, the Sagan Observatory, the program to return to Luna. Each project required money. Money was limited. Several members of Parliament, in particular Marcus Thorne from Ohio, began independently adding funding for the Aethel Voyager into the annual appropriations bills. Not because they were astrobiologists, because the mission's key contractors, including the Cavendish Applied Physics Center and the Propulsion Dynamics Laboratory, are located in their electoral districts or allied states. Jobs. This is more important than it seems. Space programs are not just about science. They are thousands of engineers, programmers, technologists. They are supply chains. They are the local economy. A politician who supports a space program supports jobs in their state. This is straightforward political logic. Therefore, the Aethel Voyager received funding not because the CSA went to Parliament and said, "We need this mission." The mission received funding because several members of parliament decided to fund it, and the CSA had to build a program around that decision. This is a decision, not a secret, and it has authors, names, dates, documents. 1996, data from the Daedalus probe's magnetometer, Vance's paper in Nature. 1998 to 99, 2001, additional flybys by the Daedalus probe confirming the ocean. 2003, the Daedalus probe is destroyed in a controlled descent into Olympus's atmosphere, intentionally, to prevent any accidental collision with Avalon and potential contamination by Terran microbes. This worked against Avalon. The mission was over. There would be no more data. 2003, the Decadal Survey's first official recommendation for the Avalon orbiter. 2004, first conceptual studies at the CSA. 2011, the Decadal Survey's second recommendation, now for the Avalon Voyager. 2013, first funding from Parliament, despite resistance from parts of the CSA. 2016, the project is officially approved and receives full funding. 2024, October 14th, launch aboard a Falcon Heavy. 2030, arrival at the Olympus System. 2031 to 2034, 49 flybys of Avalon. This is not a delay due to technical limitations. This is a queue, a funding queue with a political filter. Now, about the radiation. This is important for understanding why the mission is designed the way it is, and why it cannot be designed any other way. Olympus is the most powerful radiation system in the Helios System, after the Sun itself. Its magnetic field captures charged particles, electrons and protons, and traps them in radiation belts. These belts are structured similarly to Terra's Van Allen belts, but are incomparably more powerful. Avalon is located in the middle of Olympus's radiation zone. If you were to enter orbit around Avalon, the probe would receive about 540 rads per day. For comparison, a lethal dose of radiation for a human is about 400 to 500 rads, received all at once. The limits for electronics are different, but the principle is the same. The accumulated dose degrades semiconductors, flips memory bits, and causes glitches in the software. The Kronos mission in the Janus system accumulated a dose hundreds of times smaller. The Ares rovers operate in practically zero radiation compared to Avalon. The Daedalus probe, which spent 8 years in the Olympus system, had accumulated such a high dose by the end of its mission that its onboard electronics began to degrade. Some of the recordings on its magnetic tape were damaged. This is precisely why the Avalon Voyager does not enter orbit around Avalon. The engineers considered the options. An orbit around Avalon would have meant a lifespan for the probe of only a few months, too short for detailed science, at a cost of $5 billion. The solution: an elliptical orbit around Olympus that periodically intersects Avalon's orbit. The probe spends most of its time far from the radiation belts, receiving a minimal dose. Then it makes a rapid dive toward Avalon for a close flyby, a few hours of maximum instrument activity, and then departs again. Each flyby, a few hours of work, followed by weeks in a relatively safe zone. 49 such flybys over 4 years of operations in the Olympus system. The closest approach to Avalon, 25 kilometers above the surface. That is lower than airplanes fly over Terra. Julian Croft of the Propulsion Dynamics Laboratory is the mission's lead scientist. The budget, $5 billion. On board are 9 scientific instruments: an ice-penetrating radar, a magnetometer, a mass spectrometer, an ultraviolet spectrograph, a thermal scanner, and cameras for the visible and near-infrared spectrums. Each instrument is designed to answer specific questions. The radar, the Reason system, is designed to sound the ice. It sends radio waves deep into the ice and listens for reflections. The ice-water boundary is a good reflector. The radar must determine exactly where beneath the surface the liquid water is located, how close to the surface it is, whether there are any local pockets of water just under the ice crust. This is key information for a potential lander. The magnetometer, the same principle as Vance's in '96, but incomparably more sensitive. It will refine the measurements of the ocean's depth and salinity. It will allow the signal from the ocean itself to be distinguished from that of any other conductive layers, should they exist. The mass spectrometer will analyze material ejected into space through cracks in the ice. This is the key instrument for searching for signs of life. And this is where a story emerges, one that is almost never discussed. In 1997, the Daedalus probe was making its 12th flyby of Avalon, flyby E12. The instruments were collecting data. One of the parameters, data from the magnetometer and the plasma detector, showed an anomaly. Something was wrong with the trajectory of the charged particle streams. No one paid it much attention. Too much other data. The Daedalus probe was busy with Olympus, Hephaestus, and Oberon. In 2012, the Herschel Space Telescope photographed Avalon in the ultraviolet spectrum. In the images, plumes of vapor over the South Pole, enormous geysers ejecting water into space. The height of the plumes, up to 200 kilometers. Scientists returned to the old Daedalus probe data. Dr. Alistair Finch, Julian Croft, and their colleagues began to sift through the flyby archives, searching for the moment when the probe might have flown through such an ejection. And they found it. Flyby E12, 1997. The Daedalus probe had passed directly through a plume of water from Avalon. The magnetic field changed exactly as it should have when passing through a cloud of charged particles. The plasma became denser. The probe's trajectory deviated slightly under the pressure of the material. The analysis was published in 2019, 22 years after the flyby itself. Wait, the numbers don't add up here. The Daedalus probe flew through a water plume from Avalon in 1997. This was discovered in 2019, 22 years. Why so long? Because the Daedalus probe wasn't designed to analyze geysers on Avalon. In 1997, no one knew that Avalon even had geysers. The Herschel telescope only discovered them in 2012. Retrospective analysis is normal science. Data sits in an archive. Someone formulates a new question. Someone else goes back to the old numbers and asks, could this explain that? That's how research works. But consider the practical implications. A Commonwealth Space Administration probe flew through material from Avalon's subsurface ocean in 1997. This material likely contained everything that's in that ocean: salts, minerals, possibly organics. The Daedalus probe's mass spectrometer was working. It was measuring something. But the Daedalus probe's mass spectrometer was a device of 60s-era technology, developed in the 70s and launched in '89. Its sensitivity was incomparable to modern instruments, and it wasn't optimized to search for organics. To be specific, the Daedalus probe's mass spectrometer, an instrument called the GPMS, was designed to analyze the atmosphere of Olympus. The atmospheric probe was meant to enter Olympus and measure the composition of its gases. The GPMS was operating at the limit of its capabilities when measuring the atmosphere of a gas giant. When passing through the Avalon plume, a rarefied cloud of ice particles and molecules in open space, it was operating in a mode for which it was not intended. The results were noisy. Part of the signal could have come from the instrument itself, background contamination of the housing due to solar radiation heating. Separating the signal from the noise was extremely difficult. This is a standard story of instrumental limitations. Not a conspiracy, not a cover-up, just a 70s-era instrument doing what it could. MassSpecs on the Avalon Voyager operates on a different principle. Time-of-flight mass spectrometry with enhanced resolution. It is capable of distinguishing isotopic variants of a single molecule, of finding traces of an amino acid at a concentration of 1 molecule per billion. This is a difference of several orders of magnitude. If Avalon is ejecting complex organics into space, mass specs will detect it. In parallel, the SUDA instrument, the Surface Dust Mass Analyzer, is at work. It analyzes dust particles. Avalon is constantly losing material. Meteorites strike the surface, knocking fine particles into space. Some of these particles are fragments of the surface ice. If the surface ice contains material from the deep ocean, SUDA will see it. This is important because it's not necessary to wait for an active geyser during a flyby. The dust is always there. One more instrument deserves a separate mention. UVS, the ultraviolet spectrograph. The ultraviolet spectrograph observes Avalon's atmosphere and surface in the ultraviolet range. It was in this very range that the Herschel telescope saw the geysers in 2012. The UVS on the Avalon Voyager will detect and map all active plumes. This will allow MASSPECs and other instruments to know in advance which zone to target with maximum sensitivity on the next flyby. The coordination of instruments, that's a science in itself. The mission operates not as a collection of independent instruments, but as a system. There is another comparison that is rarely made aloud, the Kronos mission. The Kronos mission to Janus was launched in 1997, the same year the Daedalus probe flew through a geyser on Avalon. The Kronos mission arrived at Janus in 2004. And in 2005, almost immediately upon arrival, the Prometheus lander touched down on Erebus. The surface, on-site data. The development of the Kronos mission and the Prometheus lander ran parallel to that of the Daedalus probe. It was a joint project of the Commonwealth Space Administration and the Allied Space Consortium. Politically, it's easier with European partners. Scientifically, Janus is more interesting to a broad audience. Rings, Erebus with its atmosphere. But Avalon has a saltwater ocean. Since 1996, before the Kronos mission and the Prometheus lander, there was also a wait of several years. But in that case, the Prometheus lander touched down on Erebus 7 years after the Kronos mission was launched. For Avalon, it's potentially 50 years from the first data to a landing. This is not an accident and not a technical limitation. It's a systemic choice. When scientists say, we need time for development, they're right. Radiation shielding, sterilization, instrument development, all of this takes real years. Engineering constraints exist, and they are serious. They should not be underestimated. But when the first scientific recommendation came out in 2003 and the funding appeared in 2013, those 10 years were not spent on engineering problems. They were spent on political negotiations. These are different things. When they add, and we need funding, they are also right. But the gap between we need funding and we receive it, that is politics. And for Avalon, that gap was 17 years after the first scientific recommendation. The Avalon Voyager was designed specifically for such analyses. Its mass spectrometer, MASSPECs, mass spectrometer for planetary exploration, is one of the most sensitive instruments of its type ever flown to the outer planets. It is capable of detecting organic molecules in concentrations that the instruments on the Daedalus probe could only dream of. If Avalon has geysers, and it does, the Herschel telescope has shown this, the Avalon Voyager will fly through them intentionally. This is one of the mission's primary objectives. Now about what the Avalon Voyager does and what it doesn't do, and why the gap between the two is yet another political story. Now about the lander. A reasonable question. If there's a $5 billion probe, why is there no lander? A lander on Avalon would provide direct data on the surface composition, the ability to take ice samples, and potentially to open a fissure and lower a probe closer to the water. This is a fundamentally different level of information. An orbiter looks at Avalon from the outside. A lander stands on it. A conceptual lander mission was discussed. In 2017, the Commonwealth Space Administration published a preliminary report on a potential Avalon lander. The mission proposed a landing near active geysers, taking soil samples from a depth of up to 10 centimeters and analyzing biosignatures on site. The cost was estimated at $4 to $6 billion, a separate mission, a separate line item in the budget, a separate decision by the Parliament, separate years of development. In the 2022 Decadal Survey, priority was given not to the Avalon lander, but to another mission, to Poseidon. A Poseidon probe was given top priority status for the next decade. This doesn't mean a lander for Avalon will not be built. It means it's back in the queue. As of now, the lander has not been approved. The discussion continues. If you do the math, from Eleanor Vance's data in 1996 to a potential lander, if it's approved in the next Decadal Survey in 2032, if development takes 10 years, if the flight takes 6 years, we will arrive on the surface of Avalon in approximately 2048, 52 years after Eleanor Vance's data. The lifetime of a generation of scientists between a discovery and direct contact with the object. This is where the mechanics become clear, but not entirely. There is an official version for the delay. Technical limitations, radiation, the need to develop new instruments, funding queues. All of this is real. All of this is true, but it is not the full picture. There is another dimension, comparison. Ares. Since Mariner 4 in 1965, the Commonwealth Space Administration has sent more than 20 successful missions to the Red Planet. Every 2 years, a new launch window opens, and the Commonwealth Space Administration has almost always used it. Mars Odyssey, Mars Express, MER, Phoenix, the Inquisitor rover, Maven, InSight, Mars 2020. Avalon has received one mission in all that time, the Daedalus probe, which was intended for Olympus, not for Avalon. Why such a disparity? Ares is a media-friendly target. Ares is 130 to 360 million kilometers from Terra. Communication with a rover takes minutes. The flight is 7 months. Results are seen quickly. Images of red rocks, rovers driving, drilling, finding something. Avalon is 780 million kilometers away. The flight is 6 years. Radiation kills electronics. There will be images, but of white ice, not photogenic deserts. And most importantly, in the public imagination, Ares is a place where people will go. Ares means colonies, a red horizon, the future of humanity. It is easier for a politician to justify funding for Ares. It is easier for voters to understand why. Avalon is a different story. There is no picture of a future with people in spacesuits. There is the probability that something living is swimming under the ice. It's abstract. It's a hard sell. This is a decision, not a mystery, and it has a systemic logic. But let's examine these mechanics in more detail, because they repeat themselves, and not just with Avalon. In the Commonwealth, the budget for the Commonwealth Space Administration is about $25 billion a year. This is less than 1% of the federal budget. At the same time, the Commonwealth Space Administration manages dozens of simultaneous projects. The International Space Station, the Sagan Observatory, rovers, missions to asteroids, the Artemis program to return to Luna, the Herschel telescope, and planned missions to Poseidon and Oceanus. The money is distributed through a system of multi-year planning, but with annual approval in the Parliament. The Parliament grants its approval anew each year. Long-term commitments exist, but they are not protected from single-year reallocations. In such a system, expensive scientific missions are vulnerable. The Mars Science Laboratory, the Inquisitor rover, exceeded its initial budget twofold. The project was on the verge of cancellation several times. It survived because it was a media priority and because the Parliament had already invested too much to back out. This is a classic phenomenon known in budget planning as sunk cost protection. protection through funds already invested. Between 2009 and 2013, the Avalon Voyager was included in the budget proposals of members of Parliament several times, and several times the administration of the Commonwealth Space Administration removed it from its priorities. An open conflict within the system. A few members of Parliament wanted to fund Avalon, while part of the Commonwealth Space Administration preferred other targets. In 2013, parliamentarian Marcus Thorne of Ohio succeeded in getting the Avalon Voyager included in the appropriations bill with a direct mandate. The Commonwealth Space Administration was obligated to develop this mission. Not a recommendation, a legislative requirement. The agency had to comply. This is an unusual situation. Normally, the Parliament allocates money, and the Commonwealth Space Administration decides how to spend it. Here, the Parliament decided what to build. This created friction. Some scientists and administrators at the Commonwealth Space Administration believed that Poseidon or other targets were more important. The result? The mission happened. But 17 years passed between the first scientific recommendation and the funding. For comparison, from the first detection of an exoplanet by the transit method in 1999 to the launch of the Horizon Telescope, specifically designed to search for exoplanets, 9 years passed. The Horizon Telescope was launched in 2009. Exoplanets are a media-friendly topic. Thousands of new worlds. A clear narrative. A single candidate for life under ice is a different story. Harder to explain, harder to photograph. Names, dates, documents. Thorne, 2013, a line in the Appropriations Act. That's how it worked. What exactly the Avalon Voyager is meant to answer, specifically instrument by instrument. The first question, to confirm the ocean's existence via an independent method. Vance's magnetometer provided indirect evidence. The reason radar is supposed to provide direct proof, a reflection from the ice-water boundary. Gravitational measurements should show how Avalon deforms under the tidal forces of Olympus. This depends on whether a liquid layer exists beneath the solid crust. The second question, to determine the composition of the material in the plumes. The MassSpec's mass spectrometer will provide a direct chemical analysis during a fly-through of a geyser plume. We are looking for sodium chloride, already detected in the Daedalus probe's data. Hydrogen peroxide, also detected. More interesting, amino acids, fatty acids, nucleotides, molecules associated with biological processes on Terra. The third question, to find places where the ocean is closest to the surface. Chaos terrain regions, where ice plates have clearly fractured, shifted, and refrozen, are potential zones of thin ice. Those are the logical places to send a lander. The fourth question, to assess the overall geological activity. Are there zones where the ice is currently moving? Are there fresh cracks? Are there places where geysers are regularly active? The fifth question, the thermal profile. The ultraviolet and thermal spectrographs are designed to detect temperature anomalies. Warmer surface zones mean either thin ice or active processes below. None of these questions presumes a direct answer to the question, is there life there? The Avalon Voyager is a reconnaissance mission. It is gathering data for the next decision. It is important to understand this correctly. When the first flyby data arrives in 2031, the media will inevitably ask, did they find life? The answer will be no, because the Avalon Voyager is not designed to find life directly. It is designed to determine if life could exist there. The distinction is fundamental. Habitable can mean different things. Level 1, is there liquid water? Based on the Daedalus probe's data, yes. The Avalon Voyager must confirm this with direct methods. Level 2, is there an energy source? On Terra, life uses two primary sources, sunlight via photosynthesis and chemical energy via chemosynthesis. 100 kilometers beneath Avalon's ice, there is no sunlight, but tidal heating creates thermal gradients, possibly hydrothermal vents on the ocean floor. This is precisely where life has been discovered on Terra in conditions of total darkness. Archaebacteria, tube worms, entire ecosystems without the sun. Level 3. Are the necessary chemical elements present? Water, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. MassPex is supposed to determine this from the material in the plumes. If all three levels are confirmed, Avalon will be granted the status of potentially habitable. This will create scientific and political pressure for the next mission, a lander. But even in the most optimistic scenario, a minimum of 15 to 20 years will pass between the Avalon Voyager's data and the launch of a lander. It's back to the queue, back to the decadal survey, back to the Parliament. There is another consideration that doesn't usually make it into press releases: planetary protection. If life truly exists on Avalon, life from Terra must not contaminate it. This is not a hypothetical. COSPAR, the Committee on Space Research, has developed strict planetary protection protocols. Any mission to an object with potential life must either be fully sterilized or not land at all. This is precisely why the Daedalus probe was destroyed by a controlled plunge into Olympus's atmosphere in 2003, instead of simply being switched off and left in orbit, where it could have eventually crashed into Avalon. The probe weighed 735 kilograms. It carried a radioisotope thermoelectric generator with plutonium-238. If it had crashed on Avalon, potential contamination. The Avalon Voyager will also not crash on Avalon. After the mission's completion, in 2034 or later, the probe will be directed into Olympus's atmosphere. The same logic. A lander bound for Avalon will have to undergo sterilization according to Category 4 protocol, the strictest. This means heating the entire spacecraft to 135 degrees Celsius for a minimum of 48 hours. Some modern electronic components do not tolerate this well. Sterilization itself is an engineering problem that adds years of development and a significant portion of the cost. This is not an excuse to avoid the mission. It is a real constraint. And it is often underestimated when people ask, why is it taking so long? Eleanor Vance, who discovered the signs of an ocean in 1996, lived to see the launch of the Avalon Voyager. She is 89 years old in 2024. She joined the mission's science team. She saw the launch. She will not see the data. The first scientific results will not arrive before 2031. This is a resolution, not a mystery, but behind it lie 35 years of one person's work. To summarize, the Anomaly, 27 years between the discovery and the launch of a mission to one of the prime candidates for life in the Helios System. This is not a normal pace for such a discovery. The context. The Daedalus probe detected a saltwater ocean in 1996. The data was published in Nature. The conclusion was specific. Subsequent flybys confirmed it 4 times. The mechanics of the delay. It wasn't technical limitations. It was the political cue. The decadal survey recommended Avalon as a priority twice. The Parliament provided funding with a 10-year delay, and only because a few parliamentarians lobbied for it in the interest of contractors in their states. Radiation shielding is a real engineering problem, but it doesn't explain the 17-year wait after the first recommendation. Ares, as a more media-friendly and politically convenient target, received resources as a priority. The bottom line, a queue exists. It is understandable. It is explainable. But a queue where the prime candidate for life in the Helios system is waiting, that is a question of systemic values, not technical limitations. Now, an open question. The Avalon Voyager will arrive in 2030. 49 flybys of Avalon until approximately 2034. If the data confirms habitability and points to a landing site, the decision on a lander will take several more years. Development, 10 years. Flight, 6 years. Potentially, the first direct contact with Avalon's surface between 2045 and 2050. That is 50 years after Vance's data. Why is the search for life in the Helios system moving at the pace of generations, not years? And if the Avalon Voyager finds compelling signs of habitability, how quickly will the next decision be made? Faster than 27 years? Eleanor Vance made her discovery in 1996. The probe is flying toward it as of 2024. The first data will arrive in 2031. That is 35 years from discovery to an answer. There is no answer yet. Next time, the zone of avoidance. 20% of the sky is obscured by the dust of the Empyrean stream. It is there that we find the great anomaly. How scientists see what is, in principle, impossible to see directly.